All right, let's get right into it. Welcome to today's explainer, where we're undertaking a seriously fascinating mathematical journey. We are going to walk step by step through a tutorial that demystifies one of the most notoriously stubborn problems in all of mathematics, the Collatz conjecture. Now, this problem has famously baffled the absolute brightest minds since 1937, leading some to even joke that math just isn't ready for problems like this. But today we're exploring a unified proof, the Adelic resolution, by directly diving into the governing equations that finally lock this massive puzzle into place. So grab your mental notepads, because we are getting right into the heavy math.
Here is our roadmap for this deep dive. We'll start with the Diophantine obstruction, move into the universal ledger equation, tackle regime I's Archimedean ceiling and regime 2's finite dynamics, explore the analytic branch matrix theorems, and finally, bring it all together with the arithmetic resolution.
Okay, let's dive into this. Section 1, the Diophantine obstruction.
So historically, classical mathematics has just hit a total brick wall when trying to solve this conjecture. And why? Well, classical Diophantine analysis founders because it completely relies on isolated scrutiny. It traditionally isolates prime powers, trying to understand them in a vacuum. But the Collatz conjecture creates an unsolvable tension, right? On one hand, you have the division by two operations, what we call two-adic valuation or shrinkage, and on the other, you have the multiplication by three operations, the three-adic growth or expansion. Because classical math treats these as isolated discrete sequences, it simply cannot reconcile this immense non-local tension between the two scales.
To actually solve this, the framework requires a massive fundamental pivot. We can no longer view Collatz trajectories as simple, discrete integer sequences just bouncing around stochastically. Instead, we have to totally upgrade our perspective. These trajectories absolutely must be treated as global state vectors that evolve across the entire Adelic spectrum, specifically within the Adelic ring. By shifting the problem into this global arena, we stop fighting those isolated discrepancies and finally start looking at the entire system all at once. Which brings us to the math that governs it all in Section 2, the universal ledger equation. To govern this new global arena, we introduce the absolute protagonist of our story, the universal product formula. It states that the product over all places V of the norm of phi sub V equals exactly 1. This is just a beautiful piece of mathematics. What it actually dictates is that discrepancies between prime scales, like our highly troublesome 2s and 3s, are mediated globally. It enforces a rigorous consistency across all two-adic, p-adic, and Archimedean places. In this Adelic framework, you cannot just hide an arithmetic anomaly in one local place. Everything, the whole shebang, must multiply out to exactly 1. The text brilliantly refers to this as the absolute arithmetic ledger. Think of it like a cosmic accounting book. For the total arithmetic volume to balance out perfectly, to equal 1, the ledger completely prevents any non-trivial cycles from forming. Any hypothetical loop would inherently violate this perfect balance, because it would require extra arithmetic energy that the system simply does not possess.
All right, moving on to Section 3, regime I, the Archimedean ceiling.
Now that we have our ledger, we actually need to apply it. To achieve an unconditional resolution, the proof partitions the entire universe of trajectories into two very distinct regimes. For regime I, the Archimedean ceiling, we're dealing with trajectory lengths k that are greater than a critical threshold, k0. Out here, the primary engine relies on Diophantine approximation bounds to unconditionally exclude any cycles. Then for regime 2, the finite floor, we're looking at lengths k less than or equal to k0, relying instead on Adelic-Fredholm factorization and trace theory to prove stability. By splitting the problem right here, the framework perfectly targets the specific mathematics needed for each scale. When mapping this out on the local constraint spectrum, you see the finite regime bounded by solid and liquid norms, while the Archimedean regime is bounded by a mismatch metric called lambda. This strict partition at k equals k0 is really the structural key to the whole proof. It seamlessly transitions the deductive heavy lifting from asymptotic growth limits down into the governing arithmetic laws of the Adelic framework.
And this brilliantly illustrates exactly how the Archimedean ceiling works. Let's focus on that mismatch metric lambda. Lambda is defined as the absolute value of m log 2 minus k log 3. This measures the precise discrepancy between the real and p-adic scales. But the crucial part is the inequality. This metric is strictly greater than the exponential of negative c times the square of log k. This Baker-Wistholz bound mathematically proves that the arithmetic entropy required to sustain a closed loop at these massive lengths vastly exceeds the energy capacity of the underlying space. It unconditionally forbids what the text calls arithmetic wormholes. Cycles out here, literally mathematically impossible.
With the infinite horizons closed off, let's zoom in on Section 4, Regime 2, Finite Dynamics. Now, what's really interesting about this is how the deductive burden shifts completely to the finite region. Here in front I, we attack the division by two operations using solid dynamics. By applying the Mahler valuation lemma, we derive these exact Mahler coefficients, a sub n. Notice the equation here, a sub n equals -1 to the power of n minus 1 times 2 to the power of n minus 1. This gives us a highly precise two-adic valuation of n minus 1. But, to prevent spectral drift from the odd branch elements, we absolutely have to enforce a simultaneous weighting scheme, W of n. This exponentially increasing weight pushes up the valuation, enforcing a strict diagonal valuation barrier that essentially locks the system right into contractive stability. Meanwhile, Front 2 deals with the Archimedean liquid continuous regime. We can't just rely on solid dynamics, we must neutralize phase shear at the infinite place. We accomplish this by applying a weighted Sobolev approach, which yields a precise nuclear embedding constant. The sum of the approximation numbers is less than or equal to 8 pi squared. This gives us a hard trace-class ceiling of m infinity equals 2700. When combined with the solid dynamics we just looked at, we now have established uniform trace-class stability for all trajectories less than k0. Next up, arguably the densest part of the proof, Section 5, Analytic Branch Matrix Theorems. To truly secure that stability, we must completely replace stochastic observation with bounded, closed-form combinatorics. Enter the even branch theorem, which establishes a rigorous Mahler expansion. The matrix element M is defined exactly by this binomial coefficient, k choose n minus k, multiplied by 2 to the power of 2k minus n. What makes this so incredibly powerful is that it totally unifies the exact unit identity on the diagonal with the necessary valuation growth. We finally have a total analytic handle on how the even branches operate. There's no more guessing, just exact combinatorial logic. Now, the odd branch is notoriously chaotic, right? But here, it becomes fully constrained by a verified product formula. The odd branch matrix is derived from summing over a multinomial identity. Focus on the core of that, n of m, l, u. It represents a highly precise factorial fraction. This transition is just monumental for the proof. It rips the matrix elements straight out of the realm of unpredictable stochastic observation and firmly plants them into bounded, closed-form combinatorial logic. The chaos is, essentially, mathematically caged. And all of this leads us right into resolving the famous parity pattern, which is driven by Kummer's theorem. Let's look at the critical diagonal where u equals n plus 1. The dominant term argument shows that when n is even, the valuation of n plus 1 is 0. This creates a unique dominant term, forcing the overall outcome valuation to smoothly hit exactly 0. But when n is odd, the valuation of n plus 1 is greater than or equal to 1. This completely breaks that unique dominance, causing multiple summands to overlap and reach higher cancellation-dependent valuations. This perfectly and rigorously explains the observed parity behavior of the sequence using exact entry-wise valuation bounds.
Which brings us to the final synthesis. Section 6, the arithmetic resolution.
So, the crucial point is how all of these brilliant local mathematical tools seamlessly merge into a single global deductive chain. We start with uniform nuclearity, those independent decay rates we found earlier. This naturally flows into residual continuity, where the local cores pass continuously directly to the completed operator. From there, this synthesizes into the Adelic factorization, which produces an irreducible global resolution. Finally, we apply the product formula. Remember that unit content concept? It signifies a total lack of extra arithmetic volume. Because of this chain, the factorization mathematically eliminates any possible spectral capacity for deviation. Which brings us to the ultimate conclusion of the explainer. By balancing the solid two-adic dynamics of the finite regime and the liquid Archimedean nuclearity under the absolute supreme authority of the universal product formula, the arithmetic ledger is unconditionally closed. There is absolute zero spectral capacity for trajectories to deviate. Therefore, the Collatz conjecture is not just some random numeric pattern, it is a required, necessary mathematical consequence of the global reciprocity of the Adelic ring. The familiar 1-4-2 cycle remains the only permissible balanced state in the entire Adelic ledger.
The system is closed, the conjecture is definitively resolved.
We've just seen how a notoriously chaotic discrete sequence is ultimately tamed by zooming out to a global, continuous framework. And it leaves us with a truly profound thought to ponder. Could the universe's most complex discrete mysteries all ultimately bow to the continuous authority of global reciprocity? It really makes you wonder what other seemingly impenetrable math problems might be solved by shifting our perspective to the absolute ledger of the Adele ring. Thank you so much for joining me on this deep dive into the Adelic resolution. Keep questioning, keep learning, and I'll see you in the next explainer.